Hi everyone, welcome to our lecture. Today we are going to cover a lot of material. We need to finish parsing and basically syntactic analysis of programming languages. Then we will talk about names and bindings, which are basically the referencing environment, the set of all the names that are available to inside the program. And we are going to talk about the different scoping rules for names. Um, in addition to that, we said last time that we are going to talk about the homework problems. That will be later today when everybody joins the class. Currently, we don't have everybody in the class. We are also going to talk about the future homeworks. We posted all the homeworks for the entire semester. Um, we will have a homework on SML, two homeworks on parsing, followed by a homework on with Prolog. And that's all for today. We are going to finish at 12:55 today, as usual, as scheduled. So let's start the class with syntax, and then we are going to make additional recordings for names and bindings and scopes, and an additional recording for the homework issues or homework problems. So last time we talked about the different phases in syntactic analysis of programs. Basically, we talked about tokenizing. We also talked about how to transform regular expressions or to recognize regular expressions with deterministic finite state machines. Today we are going to continue our lecture with the second phase of syntactic analysis, which is parsing. So we said last time that context-free grammars or context-free languages are basically more complex than regular expressions. The time to actually solve context-free grammars for the best algorithms, the early algorithm and CYK algorithm, are relatively expensive. It's cubic time in the size of the number of tokens to the program. But there are languages for which this parsing can be done deterministically. And we mentioned that mainly we are going to talk about today about LL parsers and LR parsers. Again, this is just an overview of parsing because usually in a compiler's course we cover much more. We cover the different types of LL and LR classes of grammars. But today we are only going to go into how they actually parse strings and internally how they are implemented. Like for instance, LL parsers with table-driven parsing and LR parsers similarly with table-driven parsing, but a little bit more complicated. So let's take one grammar, and for this grammar we are going to parse the expression a comma b comma c semicolon, both with an LL parser and an LR parser. So we consider this grammar for parsing comma-separated list of identifiers separated by semicolon, terminated with semicolon, and separated with commas. So an ID list is an ID followed by an ID list tail, where an ID list tail could be either comma followed by ID list tail recursively, or it could be semicolon. And we want to see how can we construct in a parse tree the string a comma b comma c semicolon, starting from the root. So top-down parsing always starts from the start symbol, which in our case we want to identify an ID list. So we are going to start from the root ID list, and we are going to apply top-down the production rules in such a way that finally we have in the leaves only terminals, which are basically tokens identified by the tokenizer. So an ID list, we use the first production rule. There is no other production rule for ID list. An ID list is an ID followed by an ID list tail. ID is the leftmost symbol, so immediately we can actually identify that the ID that we are looking at in this on the left hand side of this string is the ID A. Now we continue. ID list tail could actually be transformed into a comma ID followed by ID list tail or semicolon. However, the next input symbol, that character or token that we have in the input string, is a comma. So we cannot use the second production rule. The comma identifies the fact that the first production rule is the only one that we can use. So an ID list tail is comma ID followed by ID list tail, and ID B is recognized. So the next symbol that we have in the input stream is comma again. So the ID list tail, which is basically the only one non-terminal that is not yet identified, must be a comma ID list tail. At this point, we also recognized C, so the next input symbol in the input stream is semicolon. So we cannot use the second production rule, we have to use the third production rule, or basically the second production rule for the ID list tail. So an ID list tail is semicolon. We identified all the tokens that we had in the input stream, and we built top-down the parse tree for ID list. Now, one thing that you would recognize from this grammar is that it's a little bit unnatural, the fact that an ID list is an ID followed by ID list tail. We could write it a little bit different in a less recursive way by saying that an ID list is an ID list followed by followed by ID followed by semicolon. In which case, an ID list tail could also be an ID followed by a comma followed by ID list. But we cannot use left recursion in LL grammars. LL grammars, from the fact that they always expand the leftmost non-terminal, would run into an infinite loop if, or basically an infinite branch, if we have left recursion in LL grammars. There are a few restrictions for LL grammars, and we are going to talk about them a little bit later. Basically, we cannot have left recursion. Different productions for the same non-terminal cannot share the same prefix, and that is because of the requirement that we want to have deterministic application of production rules. We want to know at every step which is the production rule that we can apply next. Next, a different type of parsing is LR parsing. LR parsing is a bottom-up parsing. It's basically builds the trees from the bottom until we reach the root non-terminal. So bottom-up construction for the same grammar that we saw before, and for the same string a, b, c, semicolon, the parser first finds the leftmost leaves of a tree that is an ID. Basically, it finds the ID A. Then the next leaf is a comma. Then the next leaf is an ID B, and it basically finds all the tokens and identifies them as lists. So now the input will be this list of tokens, and it will continue in this fashion, shifting all the leaves from the scanner into a forest of partially completed parse tree fragments. Basically, we have it takes all of these terminals and puts them into a stack. So the top of the stack would be semicolon, then ID C, comma, ID B, comma, ID A. Then it will start from the top of the stack. Basically, the last symbols that were seen in parsing. So it will start building this bottom-up construction of the parse tree by realizing that some of the fragments constitute a complete right-hand side of a production rule. So in our case, the first symbol on the right-hand side is a semicolon. And if we look in our grammar, semicolon is the right-hand side of the production rule that says that an ID list tail is a semicolon. So it will identify the fact that semicolon occurs on the right hand side of ideally tail, and with this right hand side it basically reduces the semicolon into an ideally tail. So we build this basically subtree that an ideally tail is a semicolon. So now it has in the stack ideally tail on the top, preceded by IDC, preceded by comma. So again, it recognizes the fact that a comma ID ideally tail, which is the current state of the stack, is another right-hand side of an ideally tail. So it replaces that comma IDC ideally tail with another ideally tail. And the process continues by reducing the next comma IDB ideally tail into an ideally tail. After doing this a couple of times, it finally can reduce the fact that in the grammar we have an ID followed by the ideally tail. It recognizes that and it builds the final parse tree. And you can see that the parse tree is built from the bottom. First it identified the right hand side is a subtree, then it identified again that the right hand side is a subtree, and the process continues until we get to the final ID list on the top of the stack. So in fact, bottom-up parsing is a little bit more powerful, but it's a little bit more complicated to implement because we need a push-down automata, and we also need for deterministic parsing not only to find what is the current non-terminal that we want to reduce and the next symbol in the input stream, and that will deterministically give us one of the production rules. But in this case, it actually has to consider the current state of parsing, basically the stack of all of these symbols that are either non-terminals or terminals on the stack. So now, when you see parsers, like for instance antler and ply and so on, you will see also a number. And that number indicates how many tokens of look ahead are required in order to parse deterministically and obtain a parse tree. Almost all real compilers use only one token of look ahead. That means that given one token from the input stream and the current state of the parser, which may be basically the current non-terminal in the parse tree or the current state of the stack, we can identify which production rule to apply next. LL grammars have a few requirements. As I said earlier, we should not have left recursion, and we cannot have common prefixes. Basically, if we have a common prefix, then with one token, we cannot determine which is the next production rule that should be applied. Also, I said that LR grammars are more powerful than LL grammars. In fact, every LL1 grammar is also an LR1 grammar. Right recursion in production rules tend to require very deep stacks and complicates the semantic analysis. So LR grammars are a little bit more complicated, but they actually are faster and more powerful for parsing. And here we have an example of an LL1 grammar. It's also an LR1 grammar. In fact, this grammar parses a program. So let's read the grammar. It basically says that a program is a statement list followed by the end of file symbol. A statement list is a statement followed by a statement list, or a statement list is empty. A statement could be an assignment statement, ID colon equal expression, or a statement could be a read ID, or it could be a write expression. An expression could be a term followed by a term tail. So again, we are using a term tail in order to represent expressions. That's always the problem with LL grammars. They are a little bit unnatural for beginners. A term tail is an add operation followed by a term tail, right recursion. or it's epsilon, it's nothing. A term is a factor followed by a factor tail. There is an extra t here that, let me correct it. A factor tail is a multiplication operation followed by a factor tail, or it's epsilon. And the factor, it's either an expression within parentheses, an ID or a number. An add operation is plus or minus, and the multiplication operation is a multiplication or division. One thing that you basically have to notice is the fact that each one of these disjunctions, in fact, is another production rule. It basically says that a statement list could be a statement or a statement list, or a statement list could be epsilon. And similarly for statement, term tail, factor, add, and multiplication. So each one of those is, in fact, it's one production rule, either if I'm using disjunction in the regular expressions. So that previous grammar captures the associativity and precedence, but most people, as I said, don't find it pretty. For one thing, the operators for a given operator, like addition, is not in the same right-hand side of a rule together. So one would like to have, for instance, that an expression is a term, or it's a term plus an expression. That would be one way to write this grammar. However, for LL grammars, it's easier to write grammars that use this term tail, that uses right recursion. However, the fact that the parsing algorithm will be very simple, and we are going to see that deterministically we can obtain easily a parser, makes up for this weakness. And in fact, the first parsers were LL parsers. Some of them were using backtracking, usually using prolog. And how do we parse a string with this grammar? We basically build a tree, parse tree incrementally. And there are multiple ways to implement LL parsing. Basically, we can keep a stack of the non-terminals, starting with the stack symbol inserted at the beginning. And we start at the top of that stack, and we try to predict productions on the basis of the leftmost non-terminal, the top of the stack non-terminal, and the current input token. So let's take an example. We have this program, which is a very easy program. It basically reads the variable A, reads the variable B, computes the sum of A and B, it writes the sum, and it writes the average of the two numbers. And we have the symbol for the end of string. So the question is, how can we use that previous grammar to obtain basically the parse tree for this program? LL parsing basically works by having a big loop which repeatedly looks up an action or a production in a two-dimensional table, where we have as the rows the current leftmost non-terminal, and as the columns the current input token. So at the beginning we have the start non-terminal, basically the root of our LL tree. And we also have the input stream. So we take the first token that we get in the input stream, we take the non-terminal, and we want to basically match a terminal. We can basically find that the current input token is a terminal that is actually used in the parsing. Or we predict a production. So basically we transform the non-terminal based on what is the input into the right-hand side of a production rule, and we insert it in the stack. Or we announce a syntax error. Basically, given the current non-terminal and the input token, we cannot match it. We basically are not expecting that input token in the program, in the parse at this time. So how is LL parsing implemented? First of all, we want to find what are all the possible tokens that can be identified for each production rule. So a program is a statement list. A statement list is a statement or followed by a statement list, or is epsilon. In which case, a program, basically if statement list is epsilon, is empty string, then a program could start with the end of file symbol. But a program could also start with a statement. And the statement could start with an ID, could start with a read statement, and could start with a write statement. So now we can basically say what could be at the beginning of a program as the first token that enters from the input stream. It could be an ID, if it's a statement, an assignment statement. It could be a read statement. It could be a write statement. So all of those are possible input tokens to our program. So we are expecting in either case that the program starts if the statement list is empty, or if the statement list starts with another statement, we are expecting as input tokens ID, read, write, and end of file. Similarly, a statement list, since it starts with a statement, or it's the empty string, it basically, a statement list could start with ID, read, and write tokens, or a statement list could start with end of file, because if a statement list is empty, then the next character that can occur, basically the next token that can occur in the file is the end of file, is the end of the program. So for every one of the production rules from 1 to 19 that we had in our original grammar, we basically can write the possible first token that can be in the input stream as an input to this production rule. So basically for the first production rule, we are basically saying that a program can start with an ID, with a read, with a write, or with the end of file. We cannot have at the beginning of a program, for instance, a plus sign or a minus sign. There are no programs for this grammar that start with a plus sign. You cannot write basically a program, a valid program input to this grammar that starts with a plus sign. So you can either build these basically sets of possible start tokens that could start the production rule top down or bottom up. Bottom up will basically means that for every production rule that starts with a non-terminal, we can actually add that token as the possible start symbol or token for that production rule. So for instance, a statement that is an assignment must start with an ID. A statement that is a read must start with a read. A statement that is a write must start with a write. An expression must start with a term, but a term starts with a factor, and the factor could start with open parentheses, ID, or a number. So for now we can basically go to the expression rule and say that an expression can start with anything that a term can start with, which is an expression can start with parentheses, open parentheses, ID, and number. So what are these useful for? They are useful for the next step, constructing a prediction table. Basically, what we are going to build is what production rule we would apply if the current input token in the input stream are the tokens that occur on the columns of this table, the production rule table, and the current top of the stack non-terminal is one of these non-terminals. So a program can only start with an ID, with a read, with a write, or with an end of file. And that basically was given in the previous step when we constructed these predicted possible inputs. In all of these cases, the production rule that we are applying is production rule number 1. So basically, given the current top of the stack non-terminal, like program, and the current token in the input stream, basically we take the original program, we tokenize it, and now we have tokens in the input stream, we predict exactly, we can tell deterministically what is the production rule that will be used for parsing. Basically, when we do parsing, we will basically represent the right hand side of that production rule as the children of the current non-terminal on the top of the stack. That non-terminal will be used now, so the right hand side of the production is now added to the stack. And we can see here, let's see for statement list. The statement list can start with ID, read and write, in which case we use production rule number 2, or a statement list could start with end of file, in which case we use production rule number 3. So a statement list with ID, read or write predict the production rule number 2, and with an end of file it tells us use production rule number 3. Now let's look at statement. Statement with an ID, use production rule number 4, with a read, use production number 5, with a write, use production rule number 6. So statement with an ID, use production rule number 4, with a read, use production rule number 5, with a write, use production rule number 6. For all of the other cases, give an error, because the current token in the input stream and the current non-terminal cannot be parsed. So the dashes basically stand for you cannot use any production rule. You should now say that this program has an error at this input token, basically in the input stream. So let's take our program that basically starts with read A, and now the first token in the input stream is read. It tells us that if we start our program and the top of the stack is the program, with a read token we apply production rule we predict that the production rule number 1 will be used, that a program is a statement list followed by end of file. And now at this point we push into the stack, we pop program, and we push into the stack end of file and then statement list. So now the top of the stack is statement list, and we basically predict the next production rule, because the statement list with a read symbol, a token in the input stream, predict the production rule number 2. A statement list is a statement followed by a statement list. So we pop statement list from the stack and we push statement list and then statement. And again, the input stream tells us that the next token is read. Read with statement uses production rule number 5. A read with a statement is a read ID. So again, we pop the statement non-terminal from the stack and we push ID and read. So now the top of the stack is a token read, and the token read is the input in the input stream. So we match read and we continue. The next top of the stack is ID, and we have the ID A on the input stream. We use that ID and we get the current state of the stack statement list followed by end of file, and the rest of the stream. Basically the next statement is read. So now again we predict that statement list with read, basically statement list with read is production rule number 2. So production rule number 2 will be used, that a statement list is a statement followed by a statement list. And we pop statement list, we push into the stack statement list and statement. And now statement with ID gives us the production rule that basically says a statement is an assignment operator. And then we push into the stack statement expression, assignment or equal, and ID. And ID is a token, so we use it with sum, and the process continues. Basically, we use the top of the stack non-terminal and the first input token in the input stream to predict what to do next. Either that we are using a production rule or that we are using a token. The moment that the stack becomes empty, we can basically finish the parsing. At that moment, we basically found the parse tree of the program. And we also built, if we actually are building a data structure, the parse tree, that the program is a statement followed by an end of file, a statement list is a statement followed by a statement list, and so on. And this tree was built top down, left to right. So we basically started with the non-terminal program. We then had statement list and end of file. Statement list is solved first into a statement followed by a statement list. Statement is solved into a read followed by an IDA, and then we solve statement list. And we continue until we build the entire parse tree for that average program that we were basically parsing. And all of this is deterministic. Basically, the non-terminal together with the input token, the first token in the input stream, tells us use a production rule or match a token. Any questions? So I wonder if the students on the chat today actually covered LL parsing in this way in CSE303, which is our Theory of Computation course, or in the compilers course, if any of you took CSE304, the compilers course. Okay. I will watch the chat. Let's see if anyone. Okay, so 303 did not go actually into details how LL is implemented, which is totally normal because it covers context-free grammars, not really how context-free grammars are implemented for special parsers, like LL parsers. So we'll talk about a little bit more about LL parsing. First of all, you cannot have left recursion in LL parsing. Basically, if you have a left recursion in LL parsing, the algorithm that I just described will be having an infinite left branch, because every ID list is transformed into an ID list followed by comma followed by ID. And now we apply the same rule for ID list, which will basically, you can see that it builds an infinite left branch. It will never terminate. However, we can get rid of all the left recursion mechanically in any grammar. So we can transform this grammar that uses left recursion into a grammar that uses right recursion. And this is why we always have this ID list tail. Basically, we start at what is the input symbol that we can have in the ID list. We can only have ID, because every ID list starts either with ID or with ID list. So an ID list starts with an ID, and then we have an ID list tail. What can occur after the ID? After the ID, we can have a comma followed by ID, followed by other ID list tails. So an ID list tail, it's either comma followed by ID followed by other ID list tails, or an ID list tail could be epsilon. This grammar, the one below, does not have left recursion anymore. It always starts with a different token, so we can basically predict which rule to use next, which production rule to use next, and it's not left recursive. So one problem we can solve mechanically in a very easy fashion. Another problem are common prefixes, because if we have a common prefix and we would like to have an LL1 grammar, we cannot have it if the current non-terminal on the stack is statement, and we have, let's say, method invocation or assignment. They both start with ID, the same token. We cannot say which one of the two production rules applies next. They both apply next. But we can eliminate these prefixes, common prefixes, using left factoring, which left factoring basically says we can add another non-terminal for the next. Basically, we can parse in one production rule all of the prefix, like for instance, a statement is an ID, followed by a new non-terminal, let's call it ID statement tail, and the ID statement tail is either an assignment statement or basically the arguments of a method invocation. So now for this new grammar, the new grammar is equivalent with the previous one. However, in the new grammar, every single rule starts, every single production rule for the same non-terminal starts with a different token. So equality versus parentheses, we know exactly if we have, let's say, method m of parentheses 1, we actually know that we have a method invocation. If we have m is equal with 5, then, or colon equal with 5, then we know that we have an assignment, and we parse deterministically in a single way, unambiguously into a single parse tree. However, even if we eliminate all the ref recursion and the common prefixes, still it doesn't make the grammar an unambiguous LL grammar. In fact, there are infinitely many LL languages or non-LL languages where mechanical transformation works fine, but the output is not an LL1 grammar. And one example is the dangling else problem. Basically, it prevents grammars from being LL1. In fact, LLK for any K, because we have ambiguity in parsing. And let's take a look at the following grammar. This grammar, basically, it's a grammar for if statements. A statement could be an if statement, starts with the keyword or the token if, a condition, which could be a non-terminal that is a Boolean condition, a then clause, and an else clause. Or maybe a statement could be other stuff, assignment statements, write, print, and so on, read, and so on. A then clause must always occur in an if statement. So it's always then statement. An else clause may exist, an else statement, or it may not exist. And if we pass in a string to this grammar, for instance, if condition 1, then if condition 2, then statement S1, else S2, there are two parse trees. In fact, this else statement can be parsed with either this if statement, or with this grammar, it may be also parsed with this if statement, and we may consider that the inner if statement has an else clause that is empty. And one thing that we said at the beginning of syntax analysis for programming languages is that you cannot have ambiguity. A program should mean a single thing. It should be parsed in a single way. It should actually be executed in a single way. So this is a no-no in parsing of programming languages. So the question is, how can we actually write a grammar? And is it common to write grammars to actually have an unambiguous LL grammar for if statements? The desired effect that we are used to from programming languages is that we would like to pair the else with the nearest if-then. So in our previous example, this else would correspond to the second if, not to the first one. So we can write an LL grammar which is a little bit less natural, in which we prefer to have inside or nested more balanced statements than unbalanced statements. So a balanced statement is an if statement that has both the then part and the else part, or other stuff that does not contain if statements. An unbalanced statement is an if statement that has a condition and a then part, but not an else part, or an if condition that has a balanced statement in the then part and an unbalanced statement in the else part. And a balanced statement is one that has the same number of then and else's, and an unbalanced statement has more thens than else's. And if you try to build the parse tree, and we could, but it will require a blackboard or a whiteboard, you can actually see that this grammar would actually parse that previous string in an unambiguous way. It basically parses the fact that the else belongs to the if statement. So this usual approach, whether top-down or bottom-up, is to, if the usual approach is not really to use that kind of complicated grammar, but actually use the ambiguous grammar together with a disambiguation rule that actually says that the else goes with the closest if statement, or more generally, the fact that the first production rule that can be applied should be used. So the most general way is actually to write the first grammar that we had, which would be ambiguous in the most general case, but the usual approach is just take the first parse tree and that's it. Prune any single other possible production that you can have. Better yet, some languages like Pascal employed explicit end markers. Like basically you have an end that symbolizes the end of the if statement that you're currently parsing. So for instance, in modular 2, for example, one if statement, the nested if statement inside ends with the first keyword end, and the other if statement is paired with the else branch and ends at the end. Ada says and if. Other languages, you can see the C preprocessor actually says phi. It's basically reverses the if statement. An if ends with a phi. One problem is that these end markers tend to bunch up in the end, because if you have a cascade of if statements, like if A is equal with B, then you do something else. If A is equal with C, then you do something else. Else, if A is equal with D, then you do something else, and so on. With end markers, this becomes basically we have at the end a lot of ends. Every single if statement that we started has to end. So we would have these if statements ended with end, basically enumerating all the possible ends. This is common actually in some languages. Having all of these ends filed at the end could be actually solved by adding a special symbol, like in functional languages based on Lisp, where you can end all the ends that you saw before with a square bracket instead of open parentheses. So let's talk about LR parsing. So LL parsing was very simple. I think by this time everybody in the lecture can actually write a simple LL parser that, given the grammar, first it unfolds the rules to find all the possible end symbols, then it would basically parse deterministically every input. Now, LR parsers are almost always table driven. Like LL parsers, they use a big loop which inspects the current token in the input stream and a two-dimensional table to determine what action to take next, reduce or shift, or actually use match a token. Unlike LL parsers, LR parsers have a non-trivial state, usually a DFA, and the table is not indexed by the current input token and the current non-terminal, but by the current input token and the current state. Also, the stack, like in the case of LL parsers, we actually stored on the stack the current non-terminal that is not that needs to be used. But the stack for an LR parser records what has been seen so far, not what is expected as an input to the parser. So LR parsers keep the root of its partially completed subtrees onto the stack. When it accepts a new token from the scanner, it shifts that token into the stack. So the parser starts very similarly to LL parsers, but immediately changes. It basically, the moment that it starts, it shifts into the stack all of the tokens one by one as basically it gets from the stack. So if we had ID A followed by comma followed by ID B followed by comma followed by ID C followed by semicolon, it will now push into the stack in order these tokens. So it pushes ID A, then it pushes comma, then it pushes ID B, and so on. This operation is called shifting. It shifts the tokens into the stack. When it recognizes the top few symbols onto the stack that they constitute the right-hand side, it reduces those symbols to the left-hand side of the production rule by popping those symbols from the stack and pushing the left-hand side of that production rule into the stack in their place. So, for instance, if our input would be A, B, C, semicolon, what LR parsing does, and we talked about this in the last lecture, you can actually look at the beginning of the last lecture, we talked about canonical derivations. First thing that it does, it takes every one of the tokens and pushes it into the stack. So we have empty stack at the beginning, it takes A from the input stream, it pushes it in the stack. Now we have in ID A, then it pushes comma, then it pushes ID B, then it pushes comma, then it pushes ID C, then it pushes semicolon. So at this point, the top of the stack is semicolon, and we basically have to use production rules to actually identify the elements from the top of the stack. So semicolon is actually the right-hand side of one production rule that basically says that semicolon, that an ID list tail could be semicolon. So we basically pop up semicolon from the stack and we push ID list tail. Now we again look at the stack and we try to identify from the right-hand side what kind of right-hand sides from basically the top of the stack, what kind of right-hand sides we can get from production rules. And we actually, with the same grammar that we had earlier, comma ID followed by ID list tail is also an ID list tail. So we pop all of those from the stack and we push ID list tail. And we do the same for comma ID B and ID list tail. We pop them and we push ID list tail. At this point, the only production rule that can be applied is that ID followed by ID list tail is ID list. And if you read in reverse order this basically derivation, we actually get a rightmost derivation. We always expand the rightmost non-terminal from our input stream, or basically from our current derivation, current sequent in the derivation. So now we actually can do it for a bigger program, and we are going to see how LR parsers work. I will be very basically explicit and simple in this case because LR parsers are a little bit more complicated than LL parsers. You can actually watch the recording a couple of times to understand how this works. So the same grammar that we had for a program, this is the same grammar that we had before. A program could be an ID list, could be a statement list followed by the end of file. A statement list could be a statement list followed by statement. We have a small change in our second rule. Basically, before we had right recursion. Now I'm using left recursion because this is an LR grammar, so I don't need to basically remove left recursion. A statement list is a statement. A statement would be an assignment, a read, or a write. An expression is a term, or is an expression followed by add operation followed by term. And again, we have a right recursion, a left recursion. A term could be a factor, or it could be a term followed by multiplication followed by factor. Again, we have left recursion. A factor could be an expression within parentheses, an ID or a number, and the add and the multiplication operations are just tokens. And the input example is the same that we had before. So when we begin the execution, the parse stack is empty, and we are at the beginning of the production for the program. So at this point, we can augment this rule, this production rule. with a period. Basically, a program is at the beginning of a statement list followed by end of list. So this new production rule is now called an LR item, is used for LR parsing. This original rule is called the basis for the current state of the parsing. Basically, a program could be at the beginning of a statement list. Since the period in this item is immediately in front of a non-terminal, that's the statement list, we may also we may be able to see the yield of those non-terminal coming up on the input. So in addition to that production rule that a program could be at the beginning of a statement list, the statement list could be at the beginning of a statement list or could be at the beginning of a statement. And we continue to augment this current top of the parsing stack. Since statement is a non-terminal, we may also be at the beginning of any production whose left-hand side is a statement. So basically, we could be at the beginning of a statement that is an assignment, a statement that is a read, and a statement that is a write. At this point, we do not have any more non-terminals that are right at the beginning of the current statement. So this set of production rules or production rules that are augmented is called the closure, LR closure for the current state of the parsing. So now we actually take the next token in the input stream. So we basically, these are the next production rules that can be applied. And now the upcoming token is a read. So we can actually look at all of these production rules, and the only one that starts with the token read is this production rule, the fifth one. So at this point we can shift the read into the stack. So we know that we are in the state that actually we identify the read, and now we are expecting an ID. This state has a single base item because the period is followed by ID and an empty closure. So there is no other rules that can be added to this parsing rule because the period precedes the terminal. So at this point we can actually take the next token from the input stream, which is A, and we can shift it into basically the stack. A statement is a read followed by ID. So now we identified read ID is the handle, and we are reducing that rule. Basically, read ID is a statement. The reduction will pop off from the parse stack and pushes a statement in their place. Basically, we take those two from the parse stack and we push into a statement. And since one of the statements in state 0 was a statement, we actually also move the parsing stack, the beginning of the statement after the statement. So a statement list is a statement. Again, we reduce. Basically, we remove the statement from the stack and we push statement list in its place. So now we are in a new state. We basically, the program identified a statement list identified a statement list, and we are now in the next possible state. And since we basically have a period which stands for the beginning or the next beginning of the input stream before a non-terminal statement, we also construct the closure. Basically, what other parsing rules can be used next? These ones, the ones that basically are for statement. And we are at the beginning of a statement. So again, we are going to shift because we basically identify another read statement. We read the next ID. We read in our program, we read B next. And here we basically have the state, the current state of the program, and the transitions. So for instance, in this case, we had the closure first constructed. Then we identified that a statement could start with a read ID. At this point, we basically identified a statement, and we actually shifted and popped from the stack read and ID. We continued, basically we used the statement, we shift it, and we actually, now at the beginning we have another statement. Again, the input symbol is a read, so we shift and we go back into state 1. A statement could be followed by ID. We read that ID and we basically return back, and we have an assignment statement, and this is the closure of the program. And the parsing continues that way. Basically, we have two stacks, one for the current rules that can be used with this period that stands for the beginning or the next token, or basically non-terminal that can be at the beginning of the program, and the stack, the parsing stack, that basically contains the next either non-terminal or token that has to be recognized on the right-hand side, and we can use a derivation. And the parsing is quite long. Basically, we build based on the state that we have in the stack, and based on the current input symbol, what is the operation that we basically apply. We can do a shift, we can do a reduce, or we can do a shift and then a reduce. Basically, shift means use the next token and actually pop it from the stack. Reduce means that take the right-hand side of the rule and pop it from the stack and push into the left-hand side of the production rule. So these are the states that we actually build out of that grammar, and this is the basically parsing table that deterministically tells us what is the production rule that we used to use for every input token and the current state of the program. The algorithm, I will skip over it, is basically this big loop that looks at what is the current top of the stack parsing rule and what is the top of the stack token, and it deterministically finds which production rule to use next. If we actually want to represent that those states in the program and the transitions for every token, this would be the equivalent DFA for that specific operation. Basically tells us at every state, we start from state 0, it tells us at every state what is, if the input token is this, what is the next state for the program. So just to summarize parsing, basically a scanner, a tokenizer is a DFA. It can be specified with a deterministic automata. An LR or an LL parser is a PDA. Usually they use push-down automata for parsing. It can be specified also with a state diagram and a stack. The state diagram looks like a DFA, but it uses the input symbol and the top of the stack, either symbol or state, to determine what is the next production rule that it should be used. The best algorithms for parsing general context-free grammars, like early algorithm, are more expensive than that. They don't use a PDA but dynamic programming, and they are cubic time. But LL and LR parsers usually have a look ahead of 1, and they use they deterministically detect what is the next production rule to use. Now we can run actions when such rules, production rules, trigger. Often we construct an abstract syntax tree for a compiler. For simpler languages, we can interpret the code directly, and we can use actions to fix the top-down parsing problems, including left recursion. But what is the goal of our class is in fact not to learn how are LL and LR grammars implemented that much. We actually need to know at least an idea, but mostly to use a compiler or tools like parser generators to create parsers, interpreters, and compilers for some form of formal description of programming languages. The input grammar for all of these compilers or parser generators is usually specified in a Bacchus-Naur form, and the generated output is the source code to a parser. So the classical parser generators were in fact Lex and Yak, and then there were more advanced versions of Lex and Yak, Bison, Flex, Antler, and so on. We are going to use Ply, which is a Python implementation of Lex and Yak. There are other Python packages that one can use for writing grammars. Those are TPG, the toy parser generator, and Antler. Antler is a Java-based parser generator like Java CC, but it also can generate Python code for that specific grammar that we write. So Lex is the original tokenizer written for Unix. It creates a C function that will basically, what's the input to Lex? They are regular expressions. And the output to Lex is a C function that will parse the input according to that set of regular expressions and will identify the tokens. Then the input from the output of Lex is basically the input for the parser. And Yak is the original parser written for Unix. It actually stands for yet another compiler. It also generates C code for a parser from BNF rules. So the input are BNF rules, grammar rules written in the Bacchus-Naur form, and the output is C code that basically uses if statements or tables to actually generate to parse an input based on that grammar. Then there are more advanced, powerful versions of Lex and Yak. They basically are re-implementations of Lex and Yak for Linux by the GNU Software Foundation. So again, the lexical rules, which are regular expressions for tokens, are the input for Lex and Yak. Lex and Yak will generate C code. The grammar rules will basically be the input for Yak and Bison, or Bison, and the output is C code, which takes the input, tokenizes it first, and then parses those tokens into a parse tree, and that's the parsed input. So all of this, basically, Yak and C generate C code to actually parse the input. So for instance, if we would have to write in Lex and Yak, we would first write the tokens in a lexer.l file, and we would write the grammar into a parser.y file, and then we will actually run Lex on that to obtain a C program that basically it's the equivalent of recognizing those tokens, and also a C program for recognizing the grammar. And here is an example of Lex. Basically, the input is what you see here as tokens. What we have here is the fact that any white space is ignored, any new line will increment the line number. The regular expression for numbers is this one. We have at least one digit, and we basically have digits from 0 to 9. In that case, the value returned as, the token that we return is number, and the value of that token is the integer. We have atom to integer of that specific text that was identified by this regular expression. Similarly, if we start with a letter or underscore, and we follow, it's followed by letters, digits, underscore, as many as possible, we basically identify an ID token. And plus stands for the plus token, minus stands for the minus token, multiplication and forward slash stand for times and division, equal stands for equals. So this would be a lexer.l file. Basically, we generate a C code if we run lex on this file to actually recognize these tokens, and output is basically the tokens and their value. Yak is very similar. Basically, we take as input the tokens, the possible tokens, and we write the production rules that specify that the star symbol is an ID equal expression. The expression could be an addition, subtraction, or a term. A term could be a number or an ID, and so on. Again, this will be the input to the Yak tool, and we actually generate a C code that parses. Similarly, for Bison, we write the BNF rules and the tokens, and it will generate C code to actually parse our input. But in this class, we are using Python. Python is one of the most modern programming languages, and it has basically implementations for Lex and Yak. Lex and Yak are quite old tools, 1970s. Ply started in 2001, and it's probably the most popular parser generator for Python. So Ply is not a code generator. Python is an interpreted language, so we don't usually run the tool to obtain Python code that basically will run, will take the input stream. We are using modules in Python. So in fact, we are using ply.lex and ply.yak. Lex is for basically computing the finding the tokens, and yak is for writing the grammar. And here we have an example of Lex first. So we import ply.lex as the current Lex, and then we define the tokens. So first we enumerate all the possible tokens, and in this list we have name, number, plus, minus, times, divide, and equal. And then we define the tokens. The regular expression for plus is a plus sign. We have to escape it because it has a meaning in regular expressions. It means it's basically a clean plus that basically requires the previous pattern repeated at least once, as many 1 to infinity, in fact. Minus is a token, and we just have minus. We can actually put it as a character. Times is the multiplication sign. Divide is / equals is equal, and so on. And then we define for each one of the tokens functions that start with t underscore. So any function that starts with t underscore is basically defines that specific token. So for instance, for number, if we recognize any sequence of digits, the value of that token is the integer part of that token, and we identify the number token. If we want, we can build the entire set of tokens by invoking lex.lex, and then the input will be actually passed to lex. So lex.input will take that input, and it will basically generate tokens. So we can get from the tokens of lex, each one of the tokens with a cursor, and each token has the following properties. Type, which basically will give us the type of the token, like name or number or plus, and so on. The matching value, which is basically, in the case of a name or ID, is a string. In the case of a number, will be a number. The line number and the position within the current line. Next, we write a parser. So again, we import a module, ply.yak. Ply.yak will basically import a yak parser. We also need the tokens, so we are going to import from the previous file that we wrote our lexer, and then we write the production rules. So each production rule is basically a function that starts with t underscore. And then we basically define the production rules. So for instance, an assignment statement, it's a name followed by equals followed by expression. The doc for that function is basically the production rule, and then we can have actions that can happen. Basically, for instance, P of 0, which stands for the output non-terminal, is P of 1 equal P of 1, P of 2, and P of 3. So basically what we are going to build is what do we assign to the output as a value based on the inputs as values. So for instance, in our program, if we actually parse the program, the output of the parse will be a parse3, because we didn't actually we didn't do anything, we just recognized the fact that we can parse that text and we didn't detect an error. So Ply uses LR parsing. It's called shift reduce parsing. We talked about it earlier today. It basically starts from the right hand side and identifies right hand sides of production rules. So during reduction, these functions are invoked. We actually identify the right hand side of the production rule, and we can actually assign a value to the left hand side of the production rule. So if the output parameter is P, then P of 0 stands for the left hand side of the production rule, and then P of 1, P of 2, and other, basically P of other increments are the right hand side of the production rule. So rules basically process from right hand side to the left hand side. The rule is stored in the left hand side, then we basically propagate this through the grammar up. These are called synthesized grammars because they actually synthesize from the leaves to the top of the tree, to the root of the tree, the value of the expression. And here we have an example. So this is a little bit long example. I will go into detail in a couple of seconds in a real parser that I've wrote and I uploaded to Piazza earlier today, or earlier on Tuesday. So for instance, the first production rule identifies an assignment. And what exactly happens during an assignment? We should compute the value of the expression and we should assign it to a mapping, basically a dictionary, that for the value of that name of variable, we store the value of that expression. So P of 1 is the name token. P of 3 is the expression non-terminal. Once we know P of 3, we can assign it as the value of the key, that is the name of that variable. Now, in the case of an expression, if we have an addition and we know the value of the first non-terminal expression on the right hand side, and we know the value of the term, which is P of 3, we can sum them and assign it to P of 0. P of 0 stands for the left hand side of the production rule. Similarly for multiplication, if we know the value of the inner term and the factor, we can multiply them to get the value of the outer term, the left hand side of the production rule. And the same applies to factor and number. Basically, if we know that the value of the number P of 1 or the factor P of 1, we assign it to P of 0, the value of the term or the factor. The same way, we can actually build a parse tree. So there are two examples that we are going to discuss about today. And those two examples, in one case, we are actually computing the value of that specific expression. In the second case, we are building a parse tree. And in this example, I'm actually using tuples to build a parse tree. So I'm creating a tuple that has the sign symbol as basically the root or the name of the parent in the tree, and then the two children that we are assigning to P1, which is a name, P3, which is an expression. Usually this is done when you have loops and you execute the same equality, like you increment x with 1 multiple times. So you cannot execute it while you are parsing it. You really have to wait until you actually execute the parse tree, and every time you execute that statement, you compute a new value of the expression and you assign it to the specific number. So In this example, we basically build a parse tree. An assignment is an assignment tree. A plus is a plus tree. A multiplication is a multiplication tree. And a number is a number that has a single child that is the value of that number. So for instance, if we would parse the same input as before, the output t is in fact a tuple. It tells us that this is an assignment, and we are assigning to x the value of plus node that has as children two multiplications. Now, we can write grammars that are unambiguous. Basically, we can actually write without needing precedence grammars that are unambiguous by actually writing a lot of rules. But in most cases, we would actually do exactly the ad hoc thing that we mentioned earlier. That we would use some precedence table that defines what is the precedence of every operator, and then we would use that precedence table to find the first rule that matches a given input in the input stream. So in ply, we can specify the precedence using a tuple in which the elements on top have the least precedence. So plus and minus have the least precedence, times and divide have higher precedence than plus and minus, and unary minus has higher precedence than times and divide. Moreover, we also specify the associativity. So plus and minus are left associative, times and divide are left associative, and unary minus are non-associative because it's a unary operator. So now we can actually specify all the parsing rules without having to take into consideration the left associativity or the right associativity or the precedence of operators. We can just write that an expression is an expression plus another expression, or it could be an expression multiplied with another expression, and the precedence will actually find the most preferred or specific parsing rule or production for that expression. The best documentation is actually the mailing list, in addition to the documentation for ply. There are other parser generators. For instance, TPG is an LL parser generator using backtracking if we actually need to use. So it's not quite LL, it's more like Prolog. It finds the first parse tree from the left-hand side, always parsing from top to bottom, but is non-deterministic. It doesn't need to basically have a non-deterministic production for every input token and every non-terminal. It backtracks if it needs to and finds the first parse tree that basically satisfies the TPG. The tokens are defined in a very similar way. We define the token and then we actually write the regular expression and the output of that token. Is basically a very powerful parser, although it's called the toy parser generator, and it's very easy to write both tokens, the way that we saw before, and to write the grammar. So this is basically a grammar for an expression, and if we actually want to write it, we can actually just add those production rules to the definition of the grammar. Okay. And there are examples in the lecture notes. Basically, we can, when we parse, we can also execute the operations that we actually define during the parsing. So in this example, in this class, we are going to use for the homework ply, or basically Python, Lex, and Yak. So let's see actually an example with Python, Lex, and Yak. Here we define the tokens. We basically we enumerate first the tokens, and then we define for each token what is the regular expression, or the regular expression and the code that gets executed for that token. We also specify the ignore characters and what happens for new line characters, or what happens if the next input cannot be tokenized, we cannot find the token for it. We can import fly.lex and basically build a lexer for that set of tokens. Basically every single either global variable that starts with t underscore or function that starts with t underscore. Next, we build the parsing rules. So in this case, I'm going to use the precedence rules to specify that plus and minus have lower priority than times and divide, which has lower priority than unary minus. Since I have variables, I create a dictionary of variables and then I specify the parsing rules. So a statement could be an assignment statement, like a name equal some expression. In which case, in the names dictionary, the value for that name is, which is t1 in the grammar, is equal with t3, which is the value of the expression. If we identify a print statement, like for instance we identified an expression or we identified a print expression, then we print the value of that expression. If we identify an expression followed by a plus followed by an expression, then we assign to t of 2, we assign to t of 0 the output of that expression, the value of t of 1 plus t of 3. And t of 2 is basically plus in that case. Same happens for minus times divide. And basically, in this case, we compute the value of the expressions on the spot. So we basically return to the parent of basically the three children, which are expression and operator and expression, the value of that expression. We have unary minus, in which case t of 0, the output, will basically be minus t of 2. T of 2 is the expression that we pass as the right hand side. We have expressions within parentheses, where the expression value t of 2 is assigned to t of 0, the output expression. We have numbers as possible expressions, in which the value of the number t of 1 is assigned to the value of the expression t of 0. We can recognize names, in which case we basically look if these names are real numbers stored in the parse tree. So in this case, the names t of 1 value is assigned to t of 0. And finally, we have p of error if we cannot parse the current stream of tokens, we detect an error by the parser. So in this case, I'm asking the user to enter a string, and then I'm parsing that string, which basically will compute the value of the expression. So the program is actually complete. If you run the program as a module, it will wait the user to enter an expression. And we can enter as complicated expressions as we like. Like for instance, 1 plus 2 multiplied with 3, it returns 7. Next, I have a different example. And this second example, actually builds a parse tree, which is the second example that we talked about in the lecture notes. So first I'm creating a class node, which is an abstract node. It basically evaluates to 0, executes nothing. Number node is a node that actually contains either a float number or an integer number. If decimal dot is found in the string value, then we actually assign to value a float number. Otherwise, we assign an integer number. When we evaluate the number, we return the value of that number. A print node, it's executed, basically given a value that is stored basically in this value node. We evaluate that value, we evaluate the node, and then we print that the value. We use the Python print to actually implement the functionality of a print statement. And then we have a binary node for expressions. So the constructor for binary node takes the current object, an operator, and two operands, v1 and v2, and stores them in the abstract syntax tree. So now, when we evaluate a binary node, depending on the value of the operator, we actually evaluate the operands v1 and v2 nodes. and we sum the two operands into the value that we return for this binary node. So that would be basically the classes that we are using for defining our parse tree or abstract syntax tree. Now we define the tokens. So in our case, we have the same tokens that we had before, except that when we create a number node, we actually a number token. The value of that number token is a number node object. Then we define the parsing rules, which for each parsing rule that starts with p underscore, instead of actually computing the value in t of 0 of that or executing that node, we actually create a node in the parse tree. So in our case, it basically for a print statement, we create a print node. For a binary operator, we create a binary node, and for factors and for numbers, we just give the values of those factors and numbers, because a number is basically a number node itself. So if we take an input, like for instance print of 1 plus 3, in fact after we tokenize it, we will see that we have as output the tokens. So we basically have print token, L parentheses, number token plus number token, right parentheses. So we identify that print statement as a series of tokens, and then we can parse it. So the result of the parse tree is in fact a parse tree. So we will actually get a print node which internally has binary node, which internally has a number node. Actually, it has the plus operator, number node, which actually contains the final value, in our case is 1, and another number node, which is 3. And then we actually, if we print the parse tree, it will actually print that this is a print node object, is the root of the parse tree. You can actually implement representation for each one of the previous objects, and then you can actually see the entire parse tree, what is internally in the parse tree. And then we can execute this parse tree. So executing it will call the method execute for each one of these objects, and will actually execute first the binary operation. First it will execute the number nodes, then the binary operation, then the print nodes. So this is an example of using ply for parsing. And in fact, the homework after the SML homework is to actually implement a parser for expressions. So next we are going to talk about the homeworks. The homework that is described here is a homework for expressions, and you can start from either the first ply example or the second ply example in the lecture notes. The next homework that is described actually should use the nodes example, the second example of ply, that actually parses first this code into a parse tree, which is built out of nodes, and then it evaluates, it executes that parse tree. So there are two homeworks that are posted, one for expressions and one for parsing, that we will discuss after a short break today. Okay? Okay, that's all for parsing and syntax. Any questions? Meanwhile, I will save the lecture and also generate the YouTube lecture to be posted later on YouTube. Thank you.